Alrighty, welcome everybody. We're going to go ahead and restart our video here. We had a couple of issues, and so let's go ahead and begin. So we're going to be going over Unit 3 multiple choice questions A and B today, and we're only going to do a couple from each section. This first section is going to be dealing with electric charge, properties of electric charge, and its conservation. So let's go ahead and look at number 1. Which of the following provides evidence that there must be at least 2 types of electrical charge, but only 1 type of mass? So as we have seen, the electrical force is way stronger than the gravitational force, such that if the universe ended up having a net electric charge, that universe would either repel or attract itself. And so as far as we see, we only ever see the gravitational attraction between materials. So what this tells us is that the electrical charge between objects in the universe cancels out. Overall, there is no net positive or negative charge to the universe as far as we can tell. And so if we look at this on the scale of the solar system, electrical forces cancel out and gravitational forces is our best answer choice. All of these answer choices here, while they are true, do not really address the question of why there are at least 2 types of electrical charge and only 1 type of mass. All right, let's go ahead and look at number 2. A scientist has claimed to have discovered a new particle that has a charge of -1/2 elementary charge. Which of the following correct statement is a correct statement about this claim? Select 2 answers. So if we look at this, we've kind of been taught that elementary charge is either going to be a +1, and that would be kind of like a proton, or -1 for an electron. And so we said that the smallest amount of charge that can exist is plus or minus an electron or plus or minus a proton. Now, it gets a little bit more complicated than that, because in reality, protons are made up of quarks. 1 proton is made up of 2 up quarks and a down quark. And what we have seen is that these guys actually happen to have fractional charge. For instance, up quarks happen to have a charge of 2/3 positive. Down quarks are going to have a charge of -1/3 of the elementary charge. Well, what we end up finding out is if we add these fractions up, we get 4/3 minus 1/3, and so the overall charge here is positive 3/3 or positive 1. If I consider a neutron, we should expect the charge of a neutron to be 0. And so a neutron is going to be 2 down quarks and an up quark. And if we do our math here, well, that's -1/3 and another 1/3 negatively combined makes 2/3, but then the up quark happens to be positive 2/3. So the overall combination here is 0/3 of elementary charge. And so it is electrically neutral. Now, as far as we see, quarks on their own are not stable. They do not exist naturally on their own. They tend to combine with other quarks such that eventually they form either whole positive energy charge or 0. So which of these answer choices is going to kind of address that? So if we look at answer choice A, it says the accepted model for representing particles requires that this particle always be paired with a second particle that has a charge of -n/2, where n is an odd integer, so that the composite particle has a charge that is an integer multiple of the elementary charge. So maybe we could combine these into 3/2, -3/2, and another -1/2 gives us a -2 charge. -5/2 and another 5/2, and another half, sorry, negatively gives us -6/2 or a -3 charge. But ultimately, as far as we know, the standard model predicts that these need to combine in such a way that we end up with a whole charge. We don't find fractional charges on their own. An error is made since it is impossible for anything to have a charge less than an elementary charge. This is kind of what we're kind of told in high school, is just that the electron is the smallest amount of charge or the quantum charge in something, but that's not entirely the case. Quarks are examples of fractional charges. C, the student must create a model for representing particles that allows for particles with charge of -1/2 of the elementary charge in order for the valid to be claimed. That's not necessarily true. We already have a model, and just by making a model doesn't necessarily make um, this claim true. For claims to be true, we need to go ahead and actually produce experiments with it that verify these claims. Because in science, a lot of times we have models, but if they don't actually predict the physical behavior, those models and numbers are meaningless. So in this case, we just produce experiments that are going to confirm or deny these claims. And so here are our best answer choices for number 2. Let's go ahead and look at number 3. Here we have 2 small conducting spheres that are hanging from insulating strings. Now, this is something called an electroscope. An electroscope is basically just some kind of object or apparatus that allows you to see if an electric charge is present. It won't tell you specifically how much charge is present. All it will tell you is whether or not it's positive and or not, or negative and or not charged at all. So they are initially in contact and they are conducting, which means that they allow charge to flow. A positively charged rod then touches the left sphere and the 2 spheres repel. So as we bring this rod here to touch, they tell us that this here is positively charged, which means more than anything that it has a deficiency of electrons. We have stripped electrons away from this object. We can't really add positive charge. All we can really do is add or remove electrons because they're on the surface of these atoms that make up these objects. So as these guys are touched, charge can flow. And so if this guy here is deficient or missing electrons, it's going to start to pull the electrons from these conducting spheres onto the rod. And so eventually what we find out is that these 2 charges are repelling each other and they hang off to the side here. And the question is, which of the following correctly identifies the charges on the left and right spheres as the 2 spheres hang as shown in figure 2? So because they are repelling, we cannot deposit positive charge, but we can remove electrons from them. And if they remove electrons from them, this guy's going to be positively charged and this guy's going to be positively charged. Their electrons were transferred to the rod, partially neutralizing it because they were in contact and they are conducting. Because they are conducting, they allow charge to flow. Just saw the chat, 1 second. No worries. Yeah. Definitely not. I know that at these times it's kind of difficult for you guys to attend these kind of like family responsibilities and dinner and stuff like that. So let's go ahead and look at number 4. So would the balls repel from the rod too? So if we don't, so like let's say, for instance, whatever, our rod here originally happened to have 5 positive charges. As it deposits a charge onto each of these, and I'm just making these numbers up, but these 2 spheres are going to gain equal amounts of charge because they happen to be the same size. So let's say these guys happen to lose, the rod happens to lose, or sorry, gain 2 electrons, so that each of these guys is now positively charged by 1. So this is going to cancel out some of that positive charge. But in this case here, if we brought in enough positive charge, if you will, it would still remain positively charged and these guys would repel, such that if I took a rod that was still positively charged, and I should probably use this in red, these guys would move away. And so they would repel each other while being repelled by the rod individually. Yes. Now, if in this case, we happen to transfer just enough electrons, let's say I barely charged the rod and I happen to bring in a rod that happened to have a charge of just 2. Actually, yeah, let's go ahead and say two positive charges. So in this case, if we happen to transfer the 2 electrons, worth of charge to make these guys positive, then this would be essentially neutral. And then in that case, chances are it would not be attracted or repelled unless this thing was a non-conductor and became polarized, which is not going to happen here because the whole idea is that it was able to draw electrons because it was, it was conducting, so to speak. Welcome, y'all. Thank you for joining. I'm just going through these questions. I guess we'll start with this one here as a poll. So, two pieces of electrically neutral tape are stuck together. The sticky side of the top piece is stuck to the back side of the bottom piece, as shown in the figure. A student pulls them quickly apart. Afterward, the student holds the backs, aka the non-sticky sides, of the two pieces near one another, and they happen to attract. The attraction, oh man, where's my cursor? We're gonna have cursor problems. This is really, we'll zoom out. Sorry if it makes it difficult to see on your screen. The attraction of the pieces is evidence of which of the following? Let's go ahead and do a poll here. Let's see what we're thinking. Oh man, I forgot to get water before we started. Okay. We'll go ahead and call it here. And so I personally have a bit of a qualm with the answer to this question because if we look at this scenario, the way I see this is this side is sticky, and stickiness in glues is due to electrostatic attraction, okay? But what's going to happen is, I guess the way I see it is if this is the sticky side, we're going to start to transfer electrons from one surface to the other. And so technically, I think that this side here would be negatively charged. And this side would be deficient, the bottom piece would be deficient in electrons, so this would become positively charged. So this is what I think should happen. But the board says that, well, at best, all you can really say is B. There are two types of charge, and these two types happen to attract each other. Because they say that you don't know for sure if the bottom piece is positive or negative. And by that virtue, they also think D would not be the best answer choice because we don't know which way the electrons are moving. I actually think C and D are both very good answer choices. And as a matter of fact, I think that D is generally a little bit better than C. I probably would have said C as my answer, but they are saying B is the best answer because that it's here more than anything, it does provide evidence that there are two types of charge that attract each other. So hopefully they don't ask something like this and it's tricky because if anything, I do think that electrons were transferred from one piece to the other. Now we could make the argument that electrons moving, that means that things are, that we have current. An electrical current generally requires a conducting material like a wire. And as far as we know, tape is essentially plastic, it's an insulator, and we should not expect electrons to move from one another in the form of current. So I could see where maybe they're thinking D is not the best answer choice. But more than anything, they say that we don't know if electrons are being moved from one to the other. And I don't like this question, but so if you got it wrong, I wouldn't be too bummed out about it. All right, let's go to number 5. The figure shows two identical, initially uncharged spheres, and they happen to be conducting. So that means that charge can move between them. Sphere B is grounded and sphere A is not grounded. A positively charged rod is brought close to, but does not touch sphere A as shown. The rod is then removed. A student claims that both spheres are now charged. Is the student correct? Why or why not? go ahead and see here what we're thinking. Okay, we'll go ahead and call it here. That's everybody. Okay, so let's go ahead and take a look here. So what does ground do? So generally, we are taught that ground is where electrons are deposited. But more than anything, think of it as a source. That means that, for instance, let's just say for whatever reason, and we'll kind of build up our solution or explanation here. Let's just say for whatever reason, I bring a rod that is positively charged here. When it's grounded, what's going to happen is electrons are going to flow from ground. They're going to come up into the sphere as I start to bring it closer and closer. Because what ends up happening is this conducting sphere is feeling an influence. And it starts to feel like there is a positive charge here, and it's going to try to draw electrons from the ground. And if I happen to make contact with this, change the color actually. If I happen to make contact with this, and while this thing is grounded, I am going to draw enough electrons into this to cancel out those positive charges. And this would get neutralized if this was still conducted to ground and I touched the sphere. If the sphere is not grounded and it is touched, like here in sphere A, let's say I happen to touch this guy and I brought in a bunch of positive charge. If they do touch, this guy is neutral at the beginning. It is uncharged. So here we're going to draw the electrons from this material, and this will end up being positive when we remove the sphere. And this might get neutralized to some extent. Now, let's go ahead and see here if I happen to bring my positively charged rod to my sphere that is grounded. So I will start to attract the electrons, and because I have and I guess kind of like the microscopic way to see it is, as I start to bring in this rod, the electrons on the sphere start to navigate this way, which starts to leave a void of electrons. Because these guys are conducting, the charge will flow and start to build up on this side here, which leaves a back region that is going to be missing these electrons. And so because it's connected to ground, that is going to allow it to draw electrons from ground into it, trying to offset that imbalance. So now let's go ahead and take a look at the question here at hand. So the rod is brought close, but never touches sphere A. So what ends up happening is no charge was transferred. The moment that we remove this rod from here, then it is back to the original scenario where this thing was not touching it or influencing these charges. So it is not going to be charged. So let's go ahead and look at C. No, when the rod is brought near, sphere A is polarized and B gains a net negative charge. Well, let's see here. So this would become polarized and the electrons would group up over here while it's close but not touching. And that would leave this region to be missing electrons and positively charged. Because the sphere is closer to this side of sphere A, well, then the electrons are also going to start moving in this direction, drawing electrons over to this side, because this is going to start drawing electrons in. We see that we have a void, and because it's grounded, the electrons will travel to it, and it's going to gain an overall negative charge. Here are all the blue negatives are all the original charge, and then red is the electrons that we drew or brought in from ground due to this void that occurred here. If this guy was grounded here, this void would draw electrons as well. So this part at the beginning is true. When the rod is removed, sphere B remains charged, but sphere A does not remain charged. So this is not going to happen. This part right here is not true. The moment that we remove this influence, these electrons are going to distribute themselves back again so that there is no charge or polarization in this sphere. So the influence that was polarizing this is gone. It is no longer polarized. Because that is no longer polarized, this guy, which had an excess amount of electrons, now wants to go back to being neutrally charged. And so the excess electrons are going to get dumped back into ground, and these guys are going to spread themselves out back again to all over the place. And so C won't work out very well, which kind of leaves us with D. No, when the rod is removed, the situation is identical to before the rod was brought near, so both spheres are uncharged. There's our answer to it. So it's just like what we had before. Okay. Question 6. A small sphere of charge of +4 nanocoulombs is brought close enough to, but does not touch an uncharged conducting sphere, which is grounded. Ground is disconnected and the small sphere is removed. Sphere A is then brought close to, but does not touch an uncharged conducting sphere. And the question is, what is the net charge on sphere B as a result of this? And the explanation for this, and I don't know if I'll be able to, yeah, does this. And what is the explanation for the charge? Let me know if we have any questions so far. All right. So if we look at this, let's go ahead and try to build up the situation. So at the beginning, this guy here is grounded, which means that it can either deposit or draw electrons. And it's originally neutrally charged. But as we start to bring in this rod, or sorry, it's another sphere that happens to be positively charged. So as this sphere here, which is positively charged, gets really close to it, and it doesn't matter from from which direction I approach, but generally we kind of just say it approaches from the opposite side of the ground, but it doesn't have to. It could be right near the ground and it would be the same effect. So even though it doesn't charge, what this tells us is that there is no charge flow between them. But as I start to create an influence of positive charge here, that is going to draw the electrons that were normally evenly distributed around here. They're going to be attracted to this positive charge region. So these guys are going to start to navigate closer to this side. Now we have polarized the sphere, but because it is grounded, while it's polarizing, that is going to start to draw electrons because this region here is going to be positively polarized. You know, we have any questions so far? Polarized. So because this region here is positively polarized, but it's grounded, the electrons from ground are going to flow to fill that void. And it's because it's a conducting sphere. Electrons flow to fill the void. Now, they tell us that the ground is disconnected. So once it's disconnected, the electrons are no longer able to flow away. They are stuck on the sphere. So here I'm going to say this part, once the ground is disconnected, the excess electrons or the electrons from ground can no longer go back. So even if we remove the sphere that was creating this influence that allowed the sphere to draw more electrons, once we remove that, these electrons would want to go back down ground, but the ground is removed. So now we are introducing a sphere with excess negative charge. And this would be A, and then B over here, and it is brought close, and it's neutral. So we could say plus, minus, minus, plus, plus, minus, something like this. Now, ultimately, the answer here is 0 because sphere B is not grounded. It has no way to pull electrons from the surroundings. At the same time, it does not touch sphere B. So the net charge here is going to be 0. And all we're really going to do is we're going to polarize sphere B. Sphere B was only polarized and was not in contact with any other object from which it could acquire charge. So what will happen is these positive charges will essentially be attracted closer to this region. These negative charges will be moving closer to this region here. And I can't move it, but hopefully we get the idea, and that's answer choice A. Let me know again if we have questions. Question 8. Positively charged insulating sphere A. So this one is insulating. That means that charge does not flow. But it happens to be charged positively because we were able to forcibly remove electrons. It is brought close to, but does not touch conducting sphere B. As shown in the figure. Uncharged conducting sphere C is brought close to B on the opposite side of sphere A. None of the spheres come in contact with each other. Which of the following correctly describes what will happen to C as it is brought near? Let me bring up my cursor. As it is brought near sphere B. So what will happen to C as it's brought close to B? What will happen to C as it's brought close to B? Okay, we'll go ahead and call it here. So let's go ahead and see here. So because sphere B is conducting, that allows the electrons to move around. And even though it was electrically neutral at the beginning, because it sees on its left side a positive influence, the electrons will migrate in this direction. So even though these electrons were evenly distributed before, like let's say I had 1, 2, 3, 4, this was before they were brought in vicinity of sphere A. But once we bring it in the vicinity of sphere A, we can go ahead and say that these guys move closer to A, which is going to create a positive charge on this side. And so to show that they're neutral, I would show 4 positive charges here for the 4 negative charges here. Well, then what's going to happen to C? Well, C is also conducting. So C is now going to see an influence of positive charge to its left. So the 4 electrons, so like the charges that were evenly distributed before, I guess I'm going to try doing this, and I don't know if it'll work. And so overall, these electrons here, oops, I missed one, are going to be shifted closer over here, which is going to leave one, sorry, yeah. So because we see positives here and negatives here overall, this is going to cause the two spheres to be attracted. They see opposite charges in each other's faces, and so, well, bam. I don't think I drew equal amounts of positive and negative, but we'll go ahead and clean this up and say we have 4 negatives and then 4 positives. Okay. Any questions so far? Go ahead and take a look at number 9. 2 identical conducting spheres on insulating stands, which means that charge cannot move through those stands, are initially far apart and contain different amounts of excess negative charge as present in the figure. The right sphere has a larger negative charge than the left sphere. The spheres are brought together, touch each other, and are separated again, but remain near each other. Which of the following represents the spheres and the resulting charge distribution on each sphere? Oh no, this guy got moved. Let me move this over. Now let's see here. Let me zoom out a little bit. So in this instance, we may want to like maybe count the charges and see, what the heck. But the main idea is that the charge is going to distribute on these two spheres because they're touching each other evenly. So A is not going to work out. They need to have equal amounts of charge. And if we look in B, C, and D, that appears to be the case. Now, which of these is the best scenario here, or the best answer? Well, we have learned that electrons repel each other. They have similar charges. And so here, B is not a very good answer choice because as they get closer and closer to each other, the repulsive force gets larger. So these guys are going to move until they can get as far as possible from each other. So D is their best answer choice. Because these guys are still near each other, that means that they can influence each other. They have an electrical influence on each other. Which means that these electrons here see these electrons close enough and are repelled. And so they're going to move in this general direction. C would be true if the two spheres were far apart from each other. And I will check the chat right now. I see we have a question. Far apart from each other. Okay, let's see here. But but if they both go to opposite sides, wouldn't the positive sides want to repel? So I think this is kind of like an extreme case, and they would want to repel each other, but the positive charge itself cannot move because the positive charge is really the nuclei of these materials. And so because they're bonded with each other, like in a metal or whatever the heck, or whatever this conductor is, they're not free to move like the electrons. And this is why we really consider current and electrical flow really just the movement of electrons. So because we can't actually move these protons, the electrons themselves are the only things that can move. And there would be some kind of repulsive force here. I do agree with that. These guys are going to exert, equal and opposite repulsive forces here. One, because they are electrically charged, and because you do have these regions of positive charge. So they would. The only thing is we don't have the positive charge moving around. And I don't know if that answered your question there. But yeah, while even though they do want to repel, the only things that can move are the electrons, and so they're just going to be the only ones that get to repel each other and pull further away. Okay. I think we're convinced on that one. If not, ask a follow-up question. Usually come up with like really clever questions like, oh yeah, I didn't think about that. Like the whole negative thing. Anyways, so question 10. Three identical conducting spheres are charged as follows. Sphere A is positively charged. Man, these questions get old, I feel. Sphere B is negatively charged with a different magnitude of net charge than that of sphere A, and sphere C is uncharged. Spheres A and B are momentarily touching together and separated. Then spheres B and C are briefly touched together and separated as well. After that series of processes is completed, which of the following interactions, if any, can be used as evidence to determine whether sphere A or sphere B had the initially larger magnitude? Oh, there we go. Okay, we'll go ahead and call it here. So let's go ahead and see here how we can tackle this. So let's say all we know is that one of these guys is larger than the other. The original charge Q0. Wow, this one is essentially 0. This one is essentially positive. Oh, sorry, negative. And this guy originally is positively charged. So let's say for whatever reason, let's say this guy happened to have 3 plus charges. And let's say for whatever reason, the negative charge only happened to be 1. 2 negative. Actually, let's do 4 just in case for this guy. And it has a different magnitude, okay? So when these guys are touched, they're going to try to neutralize each other. But because one has excess charge, this guy would probably be, is going to transfer over 2. And so we're going to end up with like maybe 2, and then this guy's going to be 0, but it has 2 positive and 2 negative. When this guy comes into contact with it, it's going to acquire some excess charge, but this guy now is going to be positive because it's going to split up evenly, even though this guy gained 2 positives now, and I probably should have done a different number here. But what's going to happen is because this is electrically neutral and this now, and I really shouldn't have said that they neutralize each other. But what will happen is we will dump some more charge onto one of these guys such that it acquires the same charge as this guy, which happened to be the same type of charge as the excess. So what ends up happening is that in reality, it cannot be determined whether the spheres will repel because they all have the same sign of charge. Which is kind of like weird because I think this question is kind of saying like the opposite of that, but kind of see what the College Board says here. So we won't know which one is positive or negative, and we won't know which one is bigger. All we will know is that, well, okay, yeah, they repel, but we don't know which one had the larger magnitude. They all will have the same type of charge. Oh, sorry, my throat's really funky. But be their best answer choice here. And they say after the series of processes, all 3 spheres will have the same sign of charge and therefore will all repel, regardless of which sphere had the initially larger charge. Let's go ahead and continue to questions B. I think these will be a little bit better. All righty, so these are from multiple choice question set B, and I figured Unit 3 has a lot of progress checks. There's 4 here, so I figured we'll do like half of each one, and then that should kind of get us going, because a lot of these questions just kind of seem repetitive. Okay, so students have 4 identical hollow uncharged conducting spheres, W, X, Y, Z. Sphere Z is given a charge of positive 40 coulombs. Sphere Z is first touched to sphere W, and then to sphere X, and finally to sphere Y. And the question is, what is the resulting charge on sphere Y? Yeah, you weren't comfortable picking the none of the above, definitely. It feels like that's seldom the answer, right? Like, but in this case, it was the case. One way you can kind of think of it is one had way too much charge, so it got distributed over, and the other guys picked up the excess, giving them all that same type of charge. Okay, let's go ahead and relaunch the polling on this one. And I think it's a little easier once we actually have numbers. Okay. So if we look at this, I think this is W, X, Y, and then this is Z. So when it first touches W, these guys are going to keep flowing. The charge is going to keep flowing until they have the same amount of charge here. And so it's going to get cut in half after they touch. Now, when we combine these two, the same thing is going to happen. The 20 and the 0 are going to combine, and they're each going to get half the charge because they're all identical. And so eventually what we get is this guy goes down to 10, and this guy gets 10. And then lastly, when we combine these here, the charge is going to get cut in half. And so each of these is now going to have 5 units of charge. So it'll be plus 5 microcoulombs. I want to make sure here, right? We didn't touch W to X and then Z to Y afterwards, right? Yeah, it is sequentially brought in contact with the other ones. Okay, so let's go ahead and look at question 2. Students have 4 identical hollow uncharged spheres that conduct, so charge moves through them. W, X, Y, and Z. The students again start with spheres W, X, and Y as they are uncharged, and sphere Z starts with a charge of plus 40 microcoulombs. They use metal rods to connect the spheres in a square whose sides are much longer than their diameters, than the diameter of the spheres. What this kind of tells us is that the repulsion of these charges isn't a big deal, but it's big enough to allow the charge to repel throughout them. This cursor situation is annoying. The students wear insulating gloves while handling the spheres and the rods. Students predict that each sphere will have 10 microcoulombs of charge. When they measure the charge on each sphere, they find that there is only 8 microcoulombs of charge on each sphere. Which of the following is most likely the cause for the difference between the student's prediction and the actual measurement? Okay, and so here, generally, we're dealing with something called electrostatics, which means that we only look at things moving, I'm sorry, charge once it has settled. We're not usually concerned with moving charge and no current. So if we look at this scenario, right, if this guy starts out with 40, then maybe 10 will flow this way, 10 will flow to this guy, and 10 will flow to that guy, and then this guy will have 10. And so that kind of makes sense. But the only way for this charge to flow is to be carried through these conductors. But if these guys are conductors, that means that they can also store charge in here. And so what we find out is that probably the best explanation for this is that some charge moved into the rods and reached a state of equilibrium. And that the charge constantly moving around the system, well, it kind of makes sense. If this was like an alternating current, the values would definitely change throughout, but we're not going to be looking at that here. Generally, especially for electrostatics, when we're dealing with these spheres, we say that it is not moving, hence the word static. Let's go to question 3. So this guy is 4 microcoulombs, this one is 2 microcoulombs, plus 2 microcoulombs, and 4 microcoulombs. The separate spheres are given the charges shown in the figure and held at the corners of a square. Which of the following relationships between the electrical forces can be explained with the concept of action-reaction pairs? Alrighty. So whenever we have action-reaction pairs, the letters or the words have to correspond. So if we're talking about the force that sphere W exerts on X, the action-reaction pair for the force W exerts on X would be the force that X exerts on W, which is not the case here. The force that Y exerts on X, well, its action-reaction pair should be the force that X exerts on Y. And so they have to have the same magnitude in all these cases. And so it turns out B is our best answer choice. And it's simply by matching X and Y in these cases. Let's go to the next one. Oops, let me unfold it here. A small positively charged sphere is brought near a large uncharged conducting sphere as shown in the figure. Which of the following best represents the charge separation of the sphere? Okay, all righty, so let's go ahead and take a look here. So generally speaking, we're going to want to go ahead and draw this charge closer. And so I think D is not our best answer choice. And so that kind of leaves us with a couple of these that look pretty good. So how are we going to tackle this idea? So let's see here. Give me 1 second. And so here, what we want to look at is the region of influence. Because we have all this positive region concentrated in this section, the electrons are going to be attracted to and travel closer to that region. And so the one that shows that best is going to be A. Now, really important, we were also kind of saying that, hey, this positive charge is not actually able to move. These charges were already there, and we happen to have some negatives here. And so these guys were the ones that navigated towards this region. I could see where B looks pretty good, but in this case, it kind of implies that the positive charge was moving, and more than anything, we should show a sense of polarization on this backside. All right, question number 8. A student created the following procedure to arrange the charges within an uncharged conducting rod so that one end of the rod and the other end is negative. And so they say, step 1, give a conducting sphere a net positive charge. 2, touch the positive sphere to one end of the conducting rod. Step 3, move the sphere far from the conducting rod. And the student finds that this procedure does not work. Which of the following modifications to one of the steps, if any, will allow the procedure to accomplish the goal of having one end of the rod be positive and the other end be negative? And we'll go ahead and call it here. So the big problem with this is that we have a conducting rod. So at best, we can induce a charge on one side to be positive and the other side be negative. The problem is that the moment that this rod comes in this sphere comes in contact with this rod, right? They say use a conducting sphere, and they say positive. Kind of clean this up. The problem with the fact that it's a conducting rod here is that the moment that these things come in contact, charge is going to be distributed evenly along the rod. It's going to spread itself out, repelling itself to the edges. And so it's really hard for us to get one end of the rod to be positive and the other one to be negative if they come in contact. So maybe we're thinking the sphere should not be removed from contact with the rod. Well, no, that's not the case. Because the moment that they come into contact, this charge is going to flow and spread itself out evenly along the surface of the rod, repelling itself. So it turns out none of these steps will allow the procedure to work as intended. At best, we could try bringing the sphere in the vicinity of it, and that would go ahead and produce a polarized effect where one side is negative and the other side is positive. But the moment we remove this from the vicinity of this rod, the charge distributes itself back over. And because it was neutrally charged, overall, this will remain neutrally charged the moment we move this away. We wouldn't, and even if it were grounded, all that would do is it would bring this charge over. But the moment we remove this influence and we get rid of the ground, the charge will distribute itself evenly on the surface because it's conducting. On a conductor, the charge is able to move evenly and spread itself out evenly over the surface. Go to number 18. Which of the following statements is true of the gravitational force but cannot is true of the gravitational force but cannot describe electrical force? Okay, we'll go ahead and call it here. So in this scenario, if we look at B, the gravitational force can be both attractive and repulsive. Automatically, that is not true. So we can knock that one out. Let's go ahead and look at A, the next one. The magnitude of the gravitational force is inversely proportional to the square of the distance between objects. This is true. So that is answering the first part. But then they want us to find a scenario that cannot describe the electrical force. Well, we have seen that the electrical force, Coulomb's law, is K, Q1, Q2, all over R squared. So it is actually able to describe the electrical force. So this part here is not addressed in answer choice A. So even though while it is true, we're trying to find a scenario where it is true to the gravitational force, but then for some reason, it's no longer, like we can't describe the electrical force. So that one's out. The gravitational force is considered to be a fundamental force. This is also true, but so is the electrical interaction or the electrical force. So that kind of leaves us with C. The influence of gravitational force dominates over extremely large scales. This is true for gravity. And while it is also true for the electrical force extends towards infinity. The problem is that for the electrical force, you need to have a noticeable or discrete difference in charge. And as far as we know, the universe is electrically neutral. And that's why we cannot describe the electrical force on the scale of the universe or a solar system, or really for everyday objects. All right, let's go ahead and look at our last one for today. 4 charged particles are fixed at the corners of a square as shown. A fifth particle of charge plus Q and mass M is fixed at the center of the square. The diagram shows the electrostatic forces on the center particle due to the other 4 particles. If the gravitational forces between the particles is considered to be negligible, the cursor. What is the magnitude of the initial acceleration of the center particle after it is released? All right, we'll go ahead and call it here. So hopefully we recognize that these forces have vertical and horizontal components. And the vertical components are going to cancel out. We have 3 F's up, 3 F's down. Even though they're at weird angles, they're symmetric. So the vertical components here are going to cancel. And really what we're going to get is the horizontal components. So we have 2f cosine theta, which is 45 degrees, 45, sorry, in this direction. And then we have another guy. So that's going to look like we have 4f cosine of 45 overall to the left. But at the same time, we have 2 counts of the force, 2f, in the opposite direction. So that's 2f cosine of 45 degrees. And so in reality, we're going to end up having a net force of 2f cosine of 45 degrees in this direction. And then we take that force divided by the mass, and that will give us the acceleration. So it really just, to kind of answer this one, we recognize that it's force per mass gives us acceleration. And then it's just a matter of comparing the forces. We have 4 counts to the left, 2 counts to the right, and that gives us a net count of 2 to the left. Alrighty, y'all, that's it for today. Thank you for making it. Hopefully that made sense and we got something out of it. Outside of that, we're done here, and we'll see you guys on Thursday for our review. And we'll also see you guys in class.